Let's review what happened so that you can evaluate how you did in answering the questions. We go back to the animation associated with our initial hotspot identification. In our panel 1, we can readily see the cold front moving southward. Behind the front, we see very strong winds with widespread gusts over 40 knots and locally above 60 knots. We also see that there is considerable cloud cover around, which makes hotspot identification particularly challenging. I'll stop the animation on the most recent frame. The best view of the hotspot of these four panels is from the nighttime fog product, which is the 10.3 minus 3.9 micron bands. We see the hotspot colored as black in this color table south of A-bar. The other three panels are this 3.9 micron band with different color tables and ranges. In this case, the hotspot is much more subtle. Note that other hotspots may exist, but may be obscured by the cloud cover. We move on to panel 2. First, note that the fire detection products on the bottom panels do not show any hotspots. The fire temperature RGB in the upper right panel does not show a signal, since the hotspot is below the detection threshold. If I move to the last frame in the animation and we focus on the NGFS RGB product, we see the hotspot right here in a magenta color. We move on to the next question, which compared CONUS sector imagery at 5-minute intervals with mesosector imagery at 1-minute interval. For the first hotspot, south of A-bar, we really don't get a signal of the hotspot. Perhaps a very subtle signature right here at 4:06 UTC on the nighttime fog product. We move on to the last frame at 4:41 UTC, and we can see the hotspot in a narrow patch of clearing just south of Clarkville that shows up best in the night fog product. We only see this on one frame at 4:41 UTC. I'll go back and forth to show that. Moving on to panel 2, again, we don't see indication of the hotspot south of A-bar early on, and we just get one frame for the hotspot at the end of animation up here at 4:41. The other panels do not detect a hotspot. Let's analyze the mesosector imagery. The early fire south of A-bar still shows up best in the nighttime fog product. However, it also shows up in the 3.9 micron band in the other three panels, likely because we have multiple frames to view the hotspot. For the hotspot south of Clarkville, near the end of the animation, notice the difference it makes to have multiple frames to detect that hotspot in the situation of a narrow patch of clearing amongst cloud cover. If we stop the animation near the end, we can first see the hotspot around 4:36 right here, but it's extremely subtle. That might be a hard sell for an initial hotspot at 4:36, but if we wait one more time, 1 minute later, we get a much more robust signal. So 4:36, if you're buying in on this very subtle signature, or if you want to wait one more minute, 4:37 UTC for initial indication from the mesosector imagery. Moving on to panel 2, the NGFS Microphysics RGB does a nice job showing the hotspots, considering the challenge of cloud cover. We stop the loop at the end of the animation, And again, it shows up the hot spot in this location. 436, very subtle, but a much more clear signal right here at 437. Next, let's analyze the radar data from Goodland, Kansas, which is roughly 50 miles away from the hotspots we've identified. As noted earlier, we recognize that other hotspots may exist, but are unable to be detected due to cloud obscuration. Sure enough, there are low CC values in this vicinity associated with a smoke plume detected on radar that is in between the other two hotspots that we've previously identified. This incident was known as the 33 fire. It was completely obscured by cloud cover until later on, and was the largest of the 3 wildland fires observed that evening. Let's look at these 3 incidents in more detail. I've compared by subjective initial detection times of the 3 incidents using CONUS versus mesosector imagery. Remember, when considering the advantage in lead time, not just the earlier image time, but also the ability to use multiple frames for hotspot confirmation versus 1 frame adds value to confidence in evaluation. You should also consider latency in AWIPS, since you see imagery display on AWIPS a little bit faster with mesosector imagery compared to CONUS sector imagery. For comparison purposes, I've listed the initial detection times from the NGFS product. Under clear sky conditions, the NGFS product should have comparable initial detection times compared to subjectively identifying hotspots from GOES imagery. However, in this case, we had a mix of scenes ranging from completely obscured by clouds on the 33 fire to mostly cloud covered on the 44 fire to partial cloud obscuration on the County Road L fire. Under clear sky conditions, the hotspot detected by GOES almost always precedes detection of the smoke plume by radar. We can see that here in the County Road L incident, even with partial cloud cover, the radar detected smoke plume was about 15 minutes after GOES hotspot detection. In the other incidents, we can see that the first indications of the fire were from the smoke plume detected on radar because of cloud obscuration preventing detection by GOES. This serves as a reminder that under the scenario of cloud cover, make use of radar for smoke plume detection. We'll discuss limitations of that a bit later, but next I want to skip forward in our case. So we move forward through 6Z. So this is panel number 2. Note that the clouds move away from the 33 fire, so we're finally able to see the associated hotspot, which is considerably larger than the other 2 hotspots. We also see the first indications of the hotspot in the fire temperature RGB in the upper right panel, as well as the fire radiative power product in the lower left panel. Note that the hotspot still does not appear in the fire temperature product in the lower right panel. The derived fire products and fire temperature RGB were designed to assess the magnitude of an existing wildland fire more so than initial detection.